Hi there. In this explainer video, we're going to be looking at an introduction to electric fields, what causes them and how to calculate them. Let's start off with one charge. We'll give it the symbol uppercase Q. Now, there's no force on this charge, is there? Until another charge is present. As soon as we put in another charge, we're going to see that there is a force that is experienced by this charge uppercase Q. And this force depends on a number of things. It depends on the distance and the direction of the displacement vector that starts from little q and goes to big Q. We'll give that the symbol R. If we move Q to another position, then the force on big Q is going to change, isn't it? Because it depends both on this distance and the direction. We can write out Coulomb's law formally, and that will actually allow us to calculate exactly the force. So the force is given by a series of constants, 1 over 4 pi epsilon naught, by the magnitude of those two charges divided by the distance squared. But it's a vector, isn't it? So it's got to have a direction too. I'm going to use the unit vector r. We'll call that r hat. That's the vector that is parallel to our displacement vector, but it has a length of 1. Okay, let's just check our notation for the moment. For our vectors, I'm going to use, there's the full vector with the arrow on top. There's the magnitude, and there's the unit vector with a hat on top. Now, if we take little q out of the picture, then of course the force on big Q completely disappears, doesn't it? So another way of describing what is happening here is by considering that little q is setting up a field of influence around it. And that field of influence is affecting big Q. We can get an idea of this field by moving big Q to different places and seeing what it feels. So we can put in our little charge and we'll try putting our test charge, capital Q, in different positions. And as we move it around to different positions, we'll see, of course, that the force on it changes both in magnitude and direction. So when it's in close, it's going to be big. The further away it gets, the smaller it gets. And notice, of course, that the direction changes as well. These arrows are showing us that there's another way of thinking about what happens to Q. If we had these pink force vectors everywhere in space, if we had that information, we could dispense with talking about little q altogether. It's called the electric field. So a field is where we assign a vector to every single position in space. And it's a really useful way of thinking about what happens to any charges, such as uppercase Q, that we put around there, while ignoring the little q, the charge that's caused the force.